I am very honored to be with all of you who are joining me tonight. What I want to do is to take you on a kind of scientific journey that's not quite finished yet, but hopefully one that will excite you in the way that it's excited me over the last almost now 2 decades. I'm going to go ahead and share my screen and start with a PowerPoint slide that kind of introduces you to a new way of doing astrophysics and cosmology, referred to as time domain astronomy. I'll say a little bit about what that means as we go forward, but just to give you the first introduction to what we're going to be talking about tonight, this evening, is to say that what we're interested in having happen is to fundamentally change the way that we look at astronomical science by having it not be just one of spatial recognition of what's out there, but also one of time. And by that, I mean how things change with time. It turns out that we have a really dynamical universe. And consequently, if we look at just static pictures, it's not giving you the full story. It would be like looking at a series of images from a movie rather than seeing the movie play out in real time. So what I want to do is to begin the journey by talking about, first of all, the history of how we came to developing an instrument that could actually do time domain astronomy, that could actually make a movie of the universe as a whole. To start with, I'm going to confess my passion and my prejudice right up front. I am an experimental particle physicist, as you heard from Armand, and that means that I had to come to astronomy as an outsider and an interloper, and I still carry the same kind of ideas as to what the science and the approach to the science has to be going forward. And so about 2004, 2005, 2006, I was very interested in understanding what would be the next discovery machine for the 21st century. And if you're an experimental particle physicist, you understand that the answer to that question is always going to be to build a bigger atom smasher, a particle accelerator, and then to build a more technically advanced detector in order to look at those collisions, in order to examine the most fundamental pieces of matter and energy that we can create. But really, around this time of 2003, 2004, I was convinced that that wasn't the way to go. And so I began looking at how other branches of fundamental physics and astronomy were going about doing their business. And I came across this very interesting project that was asking exactly the same kinds of questions that I was wishing to see answered in the experimental particle physics community, and discovering that, in fact, there were experimental particle physicists working alongside astronomers, astrophysicists, and cosmologists to figure out how to answer this question optimally. To begin with, it starts with a statement that we wanted something that was important enough that would be appealing worldwide, something that would look at science at such a fundamental level that you would have no trouble getting scientists from across the world to actually join in with the prospect of both building and then operating this machine in order to make these discoveries. The second is that we understood from a really early time in the 2000s that in order to make maximal use of the human mind, you had to expand its capacity to learn by using computers. Data science and computation at that time was growing in importance and is now, of course, absolutely fundamental to our ability to advance knowledge. We also understood that we were building a machine that was going to do basic science, fundamental research. However, if it was possible, we also wanted to understand whether it would be possible to have a machine whose science would have some form of impact on the ability for human civilization to continue on, because we understood, again, in the early 2000s, that there were fundamental threats to the existence of human civilization and even to human existence that would have to be faced by humanity at some point in the future. And the question was, can the science that we're going to do actually speak to answering some of the questions as to how we would approach solutions to the problems that are posed by those existential threats. Another thing was that I was firmly committed, as were many others, to the idea of citizens joining in with science. That is to say that we'd had decades of time in which you had to have years of training and billions of dollars in order to work at the forefront of knowledge in the big science fields, fields like high energy physics or experimental particle physics. And the question was, is it possible to actually have people who are amateurs who just have an interest in science actually join in the quest alongside the professionals in order to understand what the discoveries that you're going to be looking after or looking to find are actually going to happen. And again, we didn't know that the answer to that would obviously be yes, but we wanted to build in from the beginning a design for this discovery machine that would take into account the possibility that we could actually have citizens joining in with scientists to actually make the next leap forward. And then finally, as I think anybody who's looking at the philosophy of science quickly realizes, every question that you answer actually generates at least 2 or 3 more questions. And consequently, we thought that one of the things that we should aim for is an ambitious design that would actually get us to the point where it was quite likely, you can never have guarantees on this, but it would be quite likely that any of the answers that would come out of the questions that we attacked with this machine would directly lead us to the kinds of questions that can only be answered going far into the future, even as far as the 22nd century. And the idea here is that if you're actually asking the right questions, the deep questions, and you're making real progress at understanding those, then you're bound to be discovering things that lead you to an entirely new layer for existence, which hadn't been seen before. An example here is what I'm showing on the left with a picture that is taken from a report by the experimental particle physics community called Quarks to Cosmos, and really talks about discovery machines that can make the connection between the most fundamental building blocks of matter and energy in the universe to the very largest structures in that same universe. Now, we quickly came to a conclusion, which is that in order to do this, we could have nothing less than the entirety of the universe as the laboratory. That is, it wouldn't be possible to build a discovery machine, as I said before, like a particle collider that would answer the most fundamental questions, because you could never build one that was powerful enough to ask the very deepest questions. If we want to go to the biggest scales of energy, only the universe has gone through a stage in its existence in which you can approach energies far higher than any that we can get on Earth. Same thing with scales. What we do know from our theories that are a combination of particle physics and cosmology is that the universe started in a very, very hot, very, very small, dense, and energetic state. And consequently, if you're looking for the very smallest things, it's also going to be the case that those are likely to be found imprinted in the universe as a whole. And consequently, again, the universe has to be the laboratory. You're not going to be able to necessarily be able to create these very smallest objects, but you have a chance that those very smallest objects operating very, very early in the universe's history might have very fundamental consequences to the universe that we live in now. And we can start from really simple principles, at least simple to understand in words, why the universe might be considered as a laboratory. It begins with this statement on the left of the cosmological principle, which is that if we look on large scales, something like 300 million light years and more, the universe statistically looks the same at all locations and in all directions. And what that means is that while I don't see an exact image in one part of the universe that looks exactly the same as an image in another part of the completely different part of the universe, it is the case that if I count objects, for example, at a certain distance away from the Earth, and then I look in a completely different direction, millions of light years away, and I count the same kinds of objects, what I should see is that the statistical distribution that is, the number and the way things are arranged in relation to each other, look about the same. And what we've seen, again, from decades of study with telescopes is that this seems to be the case. That is, on the very largest scales, the universe is fairly uniform, and it looks pretty much like the same rules, the same laws of physics are operating both in distance, in direction, and also, as it turns out, in time. Now, one of the reasons we think that that is true is because on the largest scales, the law of physics that matters most is Einstein's theory of general relativity, his theory of gravity, which is that gravity has the capacity to change the direction of motion of matter and of energy. So even light is subject to gravity in the same way as an apple falling to the earth. If you have a sufficiently powerful gravitational field, you can actually see the curvature of light itself in motion from one spot to another. And what this means is that because we know the mathematics extremely well for general relativity, we can't quite solve the equations that come out of it exactly, but we can use computers to come pretty close to getting what we think is just about the same as an exact answer that we would get from pencil and paper with those equations. And so what you see here on the left is a dynamic picture of what the universe looks like, starting from a pretty diffuse and uniform state to something that looks really clumpy and has a pattern in which you see threads and clumps within those threads. And so if we understand what general relativity does to the constituents of the universe that are created at the time of the Big Bang, then we can actually ask pretty fundamental questions. As I said, the deepest questions you can probably imagine asking, which is to say that the picture that we get is pretty specific in that if we try and understand the picture here up on the top left of a very specific way in which the universe appears to us now, it depends on what was happening in the universe far back into its distant past. And we can work out with very high accuracy, we think, in theory, to really the first few fractions of a second of the universe's existence, how its development over billions of years in time proceeds to give us something that looks like what we see right now. It depends on the constituents and the constituents' densities, that is, how much there is of the stuff per unit volume. And that changes, as it turns out, over time, because things that are really light or very energetic, like these mysterious particles called neutrinos and little particles of light called photons, their density dissipates really rapidly as the universe expands. Things which are heavier, more massive, like dark matter, which I'll explain a little bit later in the talk, and atoms, which is the stuff that we're made of, that density changes more slowly, and it also, because of gravity, tends to clump together. Consequently, the density of these constituents changes as a function of the history of the universe. So we can, as I said, use the universe as a laboratory, not by virtue of being able to go back to the beginning of time and changing anything, but because from what we see right now, we can go back and change in our computations what the constituents look like as a function of the history of the universe. And those have to match pretty precisely in order to get a picture that looks like the one that we see today. Consequently, we can work out what the universe is made of and what it was like in a very detailed way, what it was made of in the past as well, by actually asking a really simple question, which is, how does gravity change the formation of structure? That is, how did we get these clumps over time? And then what's the rate at which the universe happens to be getting larger as time goes on? So yes, the universe is a laboratory, and it's one which we can understand the history of, because the further out we look in space, the further back we are looking in time. The speed of light is finite, and consequently anything that was born or died or changed billions of years ago takes billions of years for that light to transition from its original location into our eyes now. And consequently, the further back we look in time, the further out we are looking in space, the larger the volume of the universe we are also looking at. So really, every telescope is also a time machine. It allows us to not only see what things were like, but by, as I said, making specific measurements of the constituents of the universe as a function of the distance away from us or the time in the past. We can also determine the properties of the universe according to general relativity. That gives us some clue as to what things were like very, very far back in time. So what is this discovery machine that I talked about that can achieve all this? Well, it's called the Vera C. Rubin Observatory. It looks like pretty much every other big observatory that's out there in the world. It's a little different because, of course, over time, we do learn how to use the technology more effectively. So one of the things that you might notice here that you wouldn't see in observatories built, say, 20 years ago is these huge numbers of vents. Those are there in order to make sure that you can open up the space where the telescope is housed inside of this area right here. And you can come to an equilibrium of temperature with the outside so that when you pull the dome open, as you see, there's a doorway right here. The glass is very near the temperature of the outside so that it's not changing over time as the glass cools down. But other than that, this looks like a pretty standard observatory. What's special about it is the telescope. And it's a telescope that's unlike any other because it contains the most powerful camera that's ever been conceived by humankind. The site is in Chile on a high and very dry mountaintop. If you're doing astronomy, the one thing that you like to avoid as much as possible is air above your head, and in particular, water vapor, which is dissolved in that air. Chile has some of the highest and driest mountains in the world. The size, not too large. I'll compare it to other telescopes that are being built right now or soon to come online. But here's something that I'm going to talk about a little later. It's a number, may not be very meaningful to you, but this number is humongous, right? This is by far the largest degree field of view for a telescope. It sees more of the sky at any given time than any telescope ever built before. And then the number of pixels, just as in your cell phone camera, the more pixels, the sharper the image that you can collect, and the more information that you've got to deal with any kind of special effects that you want to apply to the image in order to pull out things that maybe are hidden if you simply look at the picture at first glance. The colors mean that we can take a full color image of the sky going all the way from the ultraviolet into the near infrared. The telescope itself is going to be used as part of what's called the Legacy Survey of Space and Time. Those first letters become an acronym called LSST. And LSST was the original name of the project all the way back to 2004 or so. And so you'll hear me slip into talking about LSST, even though the telescope itself has a name and the observatory in which it exists has a name. But it's the survey that's actually going to do the science. So I said I'd talk a little bit about the size of the telescope and why it's surprising. So what you see here are projects which are on the books right now to either deep in design or very close to being actually produced. The Rubin telescope, for example, the Simonian telescope, is about 2 years from having its first pictures of the sky for scientific use. And you'll see that at 8 meters, it's actually pretty tiny. It's a baby in comparison to the giant Magellan telescope, the 30-meter telescope, or the extremely large telescope. The Vera Rubin Observatory doesn't have the largest mirror, but it does have, as I said, by far the largest product of what's called the mirror area and field of size view, which astronomers refer to by this French term of étendue. But what you can think of it is telescopes are light buckets. What you want to do is to get as much light captured so you have as much information on the sky, and you want to get it as quickly as possible so that you can actually look at various parts of the sky in one night, because you've only got so many nights during the year. The étendue basically means that the largest light bucket possible for any of these is actually going to be achieved by the smallest mirror, which seems counterintuitive, but it's the optic design, and again, the incredibly accurate camera that has so many pixels in it that makes it possible to do this. So if you've got the largest camera and you've got the optic design for the telescope that can make optimal use of that camera, in fact, you do have the largest light bucket for throughput of light to data. And so what has been designed, and it's actually Stanford, the Stanford Linear, what used to be called the Stanford Linear Accelerator Center is now the SLAC National Accelerator National Laboratory, is the place where the CCD camera was built. And what you see here being held by our Education and Public Outreach, former Education and Public Outreach officer, is an image of the full moon on the CCD, right? And so you might talk about having millions of pixels in your cell phone camera. This is 3 billion, about 1,000 times larger roughly. And consequently, as I said, you've got the biggest light bucket because you've got all of this area, which for the Hubble, for example, could see only a fraction of the full moon if you were silly enough to actually point it there. And you've got all of this in one image from the LSST camera. Well, why does that matter? Well, as I said, what you want is to capture the most data possible, and I'll explain why that actually has a huge impact on the science that you can do. So what I'm showing you here looks like a very pretty background, but I'll explain that it's actually a scientific image. And what I'm showing on top of this background are these basically orange colored boxes, which are a space-based telescope that's being built, the Nancy G. Roman telescope. And then in the blue box is what's called the Hubble Ultra Deep Field. The Hubble previously has been the telescope that can see as deep into space as any telescope we've ever built. In fact, further, if you concentrate time on one area of space, it can see deeper into the universe and further back into the past than any telescope ever built before. Now, the problem is that it takes about a week or so to get as much of the area on the sky as is shown inside of the blue box. And that's because each one of your pictures is actually the white box that's indicated inside the blue box. But what you see there is that the universe, where we see this black stuff, the black areas, is not really black at all. It's actually filled with galaxies. And consequently, the deeper you go, the further back in time you see, what you see is that there's always been pretty large conglomerations of stuff going back to the very earliest time, even just a billion years or so after the universe was created. We already had galaxies that had pretty massive numbers of stars. And if we look even further, we can see that probably there's even more than we can see in this image, which is to say that there's a lot of data actually included in between the places where there are points in light for this, what looks to be a fairly typical telescope view. So consequently, what we'd like to be able to do is to have this kind of resolution, but over as much of the sky as possible at one time. But with the Hubble, we'll never get there, right? It would take years to cover even as much as the most advanced space telescope that's currently about to go into preparations for launch. However, if we look to the ground, the LSST field of view is the entire picture. Now, the entire picture for one shot of the camera won't look like that. It actually will look closer to this, and that's because even though a telescope for an existing observatory, the Sloan Digital Sky Survey, looks like this, over the course of 10 years of time, the LSST survey will produce images over the entirety of the sky at this kind of resolution. And you can see it looks very similar to that of the Hubble. So what we're talking about is looking almost as deep as the Hubble does, but with thousands of times the area that the Hubble can collect. which means that it will take a small fraction of the time to see as much as the Hubble has covered in the last 30 years. That's a lot of data, and consequently, we're going to need an international network in order to process all of it. And so the survey is set up to do that. It's got redundant pathways to take you from the mountaintop there in Chile to Florida. In one case, going directly under the sea, and another going across into Argentina, and then again under the Atlantic Ocean to get here, and then two paths to get to a central repository near the University of Illinois in Champaign, and then ultimately a data repository here again at SLAC, and then another one in Europe at a French processing site, a satellite processing center. There will also be archive sites as well as places where people can get access to large amounts of the data at once. So as far as the international part of the project, certainly there. We needed to have a consortium that was literally worldwide in order to make sure that we could not only collect the data, but process it close enough to real time to not have a tremendous bottleneck in terms of getting from observation to discovery. Now, a wide field, very deep survey is needed. And I said I would say why. And it's because the universe is dynamic. So what I'm going to do is to show you a series of pictures, all of which are things that have been discovered in just the last 18 years or so that we've been planning the construction and operation of this LSST survey. So here, for example, is called the Angel Wing galaxy. It's actually two galaxies spiral galaxies in collision, discovered just 4 years ago. This picture actually comes from just, discovery was some number of years ago, but this picture actually came from just 2 months ago. We also have supernova, and I'm going to describe 3 of them because each of them has something that's rather special about it that we didn't know 18 years ago. This one, for example, is the brightest supernova ever seen. It's from as deep in the universe as we've ever been able to see any individual object. The very brightest things that we know of that consistently shine over time are quasars, but those are entire galaxies with very active black holes at the center. So you're looking at basically the light output from billions of stars concentrated. This bright flash that's shown here in the image here is the output from one star that's outshining the billions of stars in the companion galaxy that it shares. That is something that we didn't know could actually happen. Here is what's called a hypernova. I know it's really hard to see, but with machines, with computers, we can actually pull out that there's an exploding star here. And a hypernova is something like 10 to 100 times as bright as an ordinary supernova. But we also have kilonovas, things that, again, are extremely bright, but come from a completely different process than a star that gets to the end of its life and explodes. This is actually a flash from 2 neutron stars. That is, stars that ended their regular life as stars many millions of years ago. And then because they are in binary, roughly 30% of the stars in the universe are binaries. That is, they're part of a pair. They cycled each other, orbiting, until they eventually collided. And when they collided, they produced, again, according to Einstein's theory of general relativity, gravitational waves, ripples in space-time that actually came billions of light years from the source to us. They were detected by a gravitational wave observatory, which then immediately alerted the worldwide astronomy community to turn their telescopes to the portion of the sky where these gravitational waves came from to see the dying flash that comes from those 2 neutron stars colliding together. Now, we had theories that this might happen, but this is the first time in 2017 that we actually were able to see with our own eyes that, in fact, this kind of a process actually happens. And what's also notable is that we can determine that the color here is determined by the element that is primarily produced in this collision, which turns out to be gold. So it's this process of neutron star collisions that we now have at least a good affirmation in this example is how most of the gold in the universe comes about, which we didn't really understand how that happened before. Now, if we look more locally, we also see things that are interesting and surprising and new. This is not one that we hope to see anytime at all, but we do know that eventually it will happen, which is that there are asteroids out there that share the solar system with us. And on occasion, they come into collision with the Earth. Now, that occasion, if we're talking about really small rocks, happens on a daily basis. One this large happens only on the course of millions, probably tens of millions of years. But we do understand that those collisions do happen. Here's the danger that they present. The neighborhood that we know is around Earth orbit contains rocks which are large enough, that is roughly things that are above half a kilometer in width, that are dangerous enough to actually constitute a severe threat to all of human civilization. NASA, a year and a half ago, decided to do a thought exercise, which is to say, suppose you turn to disaster experts, that we observed that there's one of those asteroids that has the Earth's name on it, and it's going to come into collision somewhere on the European continent in 6 months' time. What could you do in order to save lives? And the answer was, surprisingly, maybe not so surprising, depending on how pessimistic you are, not very much at all. The first part of the problem is that what's shown here in these red kind of elliptical eggplant shapes are the uncertainty as to where the asteroid would land. So it's not enough just to see that it's going to hit the Earth. That's something that we can pretty much do with great accuracy. We can even narrow down what side of the Earth it's going to hit. And in this case, as I said, we know it's going to hit somewhere around the European continent. But it turns out that with only 6 months to go, we've got this much uncertainty as to where it's going to land. So obviously, talking about preserving life is really difficult because the very first thing that you might imagine doing is evacuating people from that area. And of course, that's impossible given an area as large as this. The next thing is that when something hits, it turns out that the kind of blast that it makes depends a lot on what it's made of. If it's a comet, for example, those are fairly fluffy. Those give you air explosions, and air explosions can be very damaging and very widespread in terms of what they produce. But if you have an asteroid, which is considerably denser, it's going to plow into the Earth, and that's going to lift an awful lot of dust into the atmosphere, and that produces something that's referred to as nuclear winter, which is it cuts out almost all of the light from the sun, and therefore we kill off pretty much all of the plant life after just a few months of time, and we kill off a lot of the heat that's necessary to keep the surface of the Earth warm. What I'm showing here is from 2013, a dashboard, car dashboard camera of one of these comets or asteroids making an impact on Earth in Russia. So we know that it actually happens. That happened to be something that was small enough that, in fact, the explosion took place in the air and the blast wave shattered windows, but it didn't actually do widespread damage to buildings beyond that. Now, recognizing this danger from some time back, even earlier than 2013, Congress mandated NASA to make a discovery of all of the near-Earth objects with a completeness of 90% down to diameters of 140 meters by 2020. We, of course, didn't make that date because at the time that they made this, and then some number of years after, they didn't provide the actual money for NASA to carry out this mission. So it's still the case that we are nowhere near knowing 90% of all of the asteroids that are potentially dangerous enough to present a danger to millions of lives, which would mean 140 meters and up. The Rubin Observatory with our LSST expects to begin a survey in 2024 that can make a major contribution to this completeness requirement and do it within the context of the mission, because we designed in from the beginning the possibility that we would actually look at a solar system survey in order to actually catalog everything that's going on. Now, this presents a problem, however, which is that while we could say, look, we're just going to have a huge light bucket, it's going to capture pictures that are broad enough on the sky that in a length of time that's 10 years or shorter, we'll be able to take a complete survey of everything that's out there in the solar system. And consequently, any asteroids that are of danger to the Earth or potential danger to the Earth in the future, we're going to have somewhere in that data set. But the data set we're talking about is absolutely enormous. So simply having the data is not even half the problem of solving this congressional mandate. And that's because you actually have to track the asteroid, and that requires 7 pictures, not 7 or several pictures, that are taken over the span of a few days' time, a few nights' time, in order to actually see the asteroid moving against the background of the distant stars. That flash you see here is an Earth satellite that goes through the picture. And this is a problem, that you have to be looking at the same small area of the sky over several nights' time in order to actually trace that this object is moving in an orbit around the sun, and then determine how that orbit does or does not intersect with the Earth's orbit. So the typical way in which this was done was you make tracklets. That is, you have pairs of pictures taken over different nights. You try and get a little line between each one of the pairs, and then connect those little line segments out, called tracklets, to see whether or not they make a line which is consistent with an orbit around the sun as seen from the Earth. Pretty difficult to do mathematically. We've worked out how to do it, but how to get a computer to do it is actually enormously time consuming, because there are just so many objects out there, and we don't know which ones actually are asteroids, which ones are distant stars. And this idea of taking pictures over several nights' time is enormously time consuming for this precious resource of the telescope time itself. So we turn to, as I said, computation, which we knew we would need in order to be able to actually answer the very deepest questions out there. And it turns out that you can use an artificial intelligence algorithm that's well known to the computer science people, applied to a set of tasks which it's easy for a computer to actually carry out, and therefore can be done very quickly. In this case, what you do is you ask the computer to generate a number of orbits for fake objects, right? You simply have a bunch of these stored as a database, and then you simply use those as if they were real with the set of objects that are discovered in your nightly observations of the sky. Even if it's a really broad, big picture of the sky, and there might be thousands or maybe even millions of objects that shine in that picture, each one of them can be very quickly compared to this little tracklet algorithm to see whether it makes a straight line. And that line is easy for the computer to pick out of the mess of other things that happens when that orbit doesn't happen to line up with the shiny little point of light. It's also very easy to then determine from a line that you see whether or not that's consistent with being in orbit around the sun as seen from the Earth. So these two things, computers can be made or trained to do very, very quickly. This particular algorithm was created in 2018, and it is actually powerful enough that we're going to apply it to the LSST survey. And it's actually possible with this algorithm, we believe, to complete the congressional mandate of finding everything from at least 500 meters and up for certain, but maybe as far down as 140 meters as well. The survey itself is shown in this little cartoon. What I'm showing here is a picture of the sky, the entire sky, kind of like a Mercator projection for the globe of the Earth. And we're going to be located in the southern hemisphere, of course, so we won't be able to see anything in the northern sky. But what you see here is the telescope going through a kind of strange path where each little pixel that's colored in means the number of visits that the telescope has made to that area of the sky. The darker the color, the more visits that we've made. And you can see that the pattern itself doesn't look at all like you might expect, where you could say that we could just cover area of the sky, area of the sky, area of the sky in some kind of a linear or square pattern. But this pattern is very particular to optimizing the science that we want to do. And there are a number of scientific projects that are going to be underway with the LSST data. The optimization of that is done by having computer simulations of how to get the most data for as many of the science projects as you want to tackle as quickly as possible. And it turns out in order to do that, you've also got to optimize where the moon is on the sky, because you can't look anywhere near the full moon when it's up. There can be clouds. So we have to understand things about weather patterns, like how much of the sky is going to be available for each given night. All of those details are put into the computer simulation, and it turns out that the pattern that's shown here optimizes getting the most amount of data that's of the absolute best clarity over the amount of time for the survey. But over 10 years' time, you'll have something that looks like this, where red you can see is 200 visits. The lighter colors going back to blue are the least number of visits. And so you've covered a huge area of the sky. As I said, a larger fraction of the sky in 10 years than any other telescope could possibly do. After 10 years, you've got almost half of the observable sky that's been viewed more than 100 times through all 6 of the color filters. That is how you form the digital color movie of the evolution of the universe over billions of years of time. In order to do that, however, you don't have what's a typical telescope use, which is people submit ideas for how they want to do their science, which involves pointing the telescope at a particular area of the sky for a few nights of the year to collect data. They then go off and do analysis over the rest of the year. Some other astronomer comes in and makes use of the telescope to point to a different area. In this case, 90% of the observing time has to be dedicated to doing the survey, as I just showed you in the cartoon on the previous slide. Every 3 nights or so, the whole southern sky will be scanned twice per night. Over 10 years of time, that produces something like 1 billion images. Those images produce 100 petabytes. A good way to think of the scale is the hard drive that I have on the computer that I'm using to show you this presentation right now is about 1 terabyte. And so what we're talking about is something that's 100,000 times the size of the hard drive on my computer. And that's just for the raw data. When we talk about processing that data in order to pull out identifications of things like galaxies and individual stars and novae and supernovae and so forth, we are pretty much guaranteed to almost double that. And then when we talk about the simulated data that we're going to compare, as I said, one of the ways that we can use the universe as a laboratory is to compare what we see now and what we saw in the past to our models of how general relativity takes the constituents from the very earliest time and evolve the universe. And so again, we increase that data set even more. So in this case, we're going to have 20 billion identified galaxies, 17 billion individually identified stars, by far the largest data set of either of those produced. And here's what we do with it. So the discovery, the one I'm most interested in, is dark energy and dark matter, but we have other discovery things that we're looking at. For near-Earth objects, we'll have up to 6 million minor planets discovered through this survey, and it's by far the most cost-effective solution to discovery of all the Earth-crossing orbits, because we've already done the computer science that's necessary to make use of the data, and we've already built the instrument. It's pretty much complete now. We're just waiting for final assembly. And consequently, the survey is going to go on without having to put in any more money from NASA for a dedicated mission. It's still necessary to do other things, which I'm not going to go into, or technical details around data mining. And then, as I said, it's a pretty essential thing that we designed in from the very beginning to have STEM education and public engagement as part of the mission. So I said that I'm interested in dark energy and dark matter. So let's talk a little bit about what those are. Okay. So dark energy we can think of as just something mysterious. We don't understand the underlying physics that makes it possible, but it causes the universe to expand at a faster and faster rate. That's what it does. And we don't actually know what it is, but if we can define what it does to ever finer resolution, that is more and more accuracy, the hope is that we're going to have something pop out in terms of the specific properties of dark energy that are going to give us a clue as to what the fundamental physics is. But in order to do that, we have to have extremely accurate measurements of the expansion history of the universe going far back into the universe's evolution. One way to do that is to use a particular kind of exploding star referred to as a type 1a supernova. I won't go into any details as to what that is, but as I said, many stars in the universe are born and live out their existences as binaries, and so they can have different lifetimes. And so it's possible that one of them can die and become a neutron star. It's exhausted all of its fuel. It compresses down to a very, very small volume object with very high gravity, and its still living companion can have matter stolen from it by that tremendous gravity. That matter builds up, that's fuel, on the surface of the neutron star until it gets to the point where you initiate a thermonuclear explosion. This is basically just a big H-bomb. It's large enough that this is one of the more powerful explosions that happens in our universe since the time of the Big Bang. The explosion is big enough that it destroys actually both objects. And it's bright enough, therefore, that we can see it from billions of light years away. Now, it turns out that, again, because we know from Einstein's theory of gravity what the expansion of the universe should look like, we can use these explosions as standard candles. That is, they put out a specific amount of light. That light dies off as 1 over the distance squared. And consequently, we can look to see the comparison of how much light we received to how much we expected was produced at the source at the time of the explosion. We can also, for the first time, have a large enough sample of quasars, which are the cores of galaxies that are very, very active in the distant past. Again, they're among the brightest objects in the universe. And so they also allow us to use them pretty much as standard candles in order to determine, first of all, how fast the universe was expanding at that time from something called the redshift. And from the brightness, we can determine how large the universe was at that time. Consequently, mapping this out allows us to determine the difference between, say, the black curve, which is the thing that we might produce in a universe which has no dark energy, and the purple curve, which is something that has a fair amount of dark energy that's increasing with time in a particular pattern. And by, again, determining with very, very accurate data which of these two curves you can see are very close together happens to describe our universe, gives us the properties of dark energy at far more accuracy than we've ever had before. Now, what's crucial to this is the statistics. And for the LSST, we're going to have about 10 million quasars discovered. Again, just sitting in the data set. What we need to do is to simply come up with the artificial intelligence algorithms that allow us to pick it out. We can also look at the history of structure formation, because I said I was interested in dark matter, but dark matter doesn't produce light. So how do we see it? Well, it turns out that the one way that we know that we can see it, and it's the only way right now, is by the gravity that it produces. And that's because, as I told you earlier, Einstein's theory distinctly predicts that gravity bends the path of light that goes near very massive objects. That bending of the light acts like a lens, a piece of glass that's curved in a particular way. By looking at the distortion, therefore, of a background image, like a bright blue galaxy, we can tell where we are, what the distortion is. We do it with statistics. I won't go again through the math. It's pretty complex, but very straightforward in the sense that the math in and of itself has to be right? It's basically geometry, the relationships of objects to each other in space. And consequently, if we look at that distortion, we can determine how much gravity there is in the foreground, here in the gray area, no matter whether it produces light or not. So all of the bright galaxies, for example, produce a certain amount of distortion, but the amount of light that they put out is indicative of the number of stars that are there. And knowing the mass of the average mass of stars, we can weigh them by simply looking at how much light they put out and the kind of light. But the stuff that's invisible has to be responsible for all of the distortion that occurs that can't be accounted for by all of the bright stuff. Consequently, even if you're invisible, you can't stay hidden. We can look not only at the amount of dark matter that's out there, but the distribution of it. How is it geometrically situated with respect to the bright stuff that's there? And consequently, by looking at this as a function of time, that is looking further back into the universe, again, we have to be able to see things that are very, very far away. That's why LSST has to be able to make such deep pictures. Consequently, we can actually determine how dark matter arranges itself from its own gravity and how its gravity helps arrange the luminous matter as well. And consequently, we can narrow down the characteristics of the dark matter, hopefully well enough that we can tell the physicists with great accuracy how they have to look for it. And that, of course, would get us around a really frustrating problem, which is the room you're sitting in right now is suffused with dark matter. It's passing right through our bodies, right through the room, right through the air, and into the earth all the time. But it is so resistant to interacting with normal matter that we've not yet found a single experiment that's able to predict, that is able to actually produce even one event from an interaction of dark matter and normal matter. But if we could actually determine the properties of dark matter, like the mass of the particle that it's composed of, that would help a lot. So what I'm giving you here is just a summary for the people who want to go into the science. I can say a lot more about each of these in the questions, but it's basically a really broad spectrum of stuff. Dark matter, the properties of dark energy. The transient sky is pure discovery, right? We will find things that we never knew existed before. As I said, just the varieties of supernova we've discovered, explosion mechanisms that we never caught on camera before, all discovered in the time that it's taken for us to actually design and build the Vera C. Rubin Observatory. Those are all discovered by telescopes that have only a tiny fraction of the area of the sky in their data set that LSST will have. A complete inventory of the solar system down to very small sizes, and an inventory of the Milky Way. Again, over the same 18, 20-year period of time, we've discovered that the Milky Way itself is also fairly dynamic. It has actually eaten a number of smaller galaxies in order to produce the structure of the Milky Way that we see today. And then finally, the composition of the universe, having the most accurate picture of where we sit in terms of ordinary matter, and dark energy. The data to knowledge, well, that we can do. This is a picture for the experts, but simply to say that we will need to make 20 trillion measurements per night in order to keep up with the data that's coming in every night from the observatory. And so we've designed a system that is actually capable of doing that. Well, what about education? Well, first is that we will have alert packets of transient and variable data derived every night, which will be available to the public immediately. And when I say the public, I mean anyone with a web connection. The education and public outreach was planned with the same level of care as the telescope itself, as well as all of the data analysis tools. All of this has been planned in. And so there are 4 various audiences that we've planned to actually make possible to look at the data. The general public will simply be able to look at the website and get a listing of all the things that were discovered in the previous evening. Formal educators will be able to make use of tools that are being provided by the project in order to come up with educational projects for students. Planetariums and informal science centers will be able to actually pull up even more detailed data. And then everyone in the world will be able to write on a web form a proposal for what they think is interesting to look for in the universe, have that put into the set of things that are examined in those 20 trillion measurements per night, and get an output every morning of the things that have been discovered in the LSST data set. So we really will be able to empower citizen scientists. We know that that's true because we've partnered with Google to store all of the astronomy data in the cloud. And then finally, we've taken it as very serious that we need to create the next generation of scientists, not just the next generation of answers to science questions. And so I, for some time now, have been a member of the LSST Corporation, which is a nonprofit that raises money from other nonprofits in order to both make it easier for scientists to actually make use of this torrent of data, but also to create the next generation of data scientists specializing in astronomy and astrophysics. So we've created an LSST interdisciplinary network for collaboration and computing, also called LINC, that is creating and sharing analysis tools for meeting the key LSST science goals, which I showed you before, the 4 goals, the training and mentoring of future scientific leaders, and more importantly, making sure that since we're doing new science in a new way with a completely new instrument, that we open up possibilities to far more people than have ever been invited before. So we have explicitly put together a plan and have now got funding for opening the discovery space to a far larger and a far more diverse community of scholars than we could ever have expected, because generally these projects are led and actually mostly guided by the top institutions around the world. Those institutions in and of themselves have not succeeded in producing a very diverse set of people who are interested in astrophysics and particle physics. And consequently, we've taken it on as a goal to actually make sure that this huge torrent of data that's available to everybody around the world goes into the hands of a set of people who've got key training in order to make sure that they can be leaders in this community. Finally, I just think it's important to note that this is the first observatory named for a woman astronomer, Vera Rubin. You see the picture of her in 2002. She is the scientist who is most singularly responsible for our belief in the existence of dark matter. And so it's entirely appropriate that this incredible instrument is being named in her honor. And with that, I will stop and I'll be happy to answer any questions that are in the Q&A.
All right, great. Thank you, Larry. That was awesome. Like Larry said, you guys can hop into the chat at the bottom, the Q&A button. That's where you can type in your questions and we'll start taking them from there. I already see a couple in here, so we'll start off right from the top. Question here says, early on, was there no dark energy, or is it just that people haven't detected effects that would pertain at an early time?
So the answer is that really early on, there was essentially no dark energy. And that's because as far as we can determine thus far, and this is why we need to have even more accurate determinations of the properties of dark energy is a property of space itself. So when the universe was small, there wasn't very much space, and consequently, there wasn't much dark energy. The more space expanded, because dark energy is a property of the space as it's being created, you're creating more dark energy over time, and consequently, it now dominates. It's about close to 70% of the total mass energy. And as far as we know, unless something we discover causes us to change our mind about it, that dark energy is going to come to just completely dominate everything else. And consequently, it already dwarfs dark matter. Dark matter and normal matter will become just not even a correction on the effect of dark energy's gravity on the expansion of the universe. So for right now, it's true that there wasn't much because it's a property of space, and there just wasn't as much space very, very early in the universe's history.
Wow, that's super interesting. So another question here says, the Planetary Society has a project to protect from asteroid impact. Do you think this could be productive?
Absolutely. And so one of the things I should have mentioned, forgive me for not doing that, is that we have close to about 50% of the Earth orbit crossing planetesimals, as they're called, identified now. Really a huge number of those, a really large fraction of those, were discovered by amateur astronomers with very tiny backyard telescopes. Consequently, with the LSST, we do hope to empower this very same community, perhaps one that's even larger, as a way of pulling people into just the science of astronomy, to make use of their work. So there will be a very powerful computer AI guided effort to try and pull out the really dangerous asteroids. But there will be a number that will be discovered in the data set by people who are just interested in understanding, what can I see? And they're going to be the ones who, before we get around to processing all the data, are going to spot some of these asteroids.
Yeah, and I guess like along those lines, it's from the same person. It says, when we do have that data, for example, but you said the population could not be evacuated and civilization saved. So what do we plan to do with the data, I guess, that would empower us to do something?
Okay, so the biggest thing we can do is not wait until 6 months before collision time to actually discover that this is going to happen. So while certainly it won't be up to LSST scientists to work out what you would do to try and deflect an asteroid, it's very easy physics to figure out that the sooner you know that it's going to impact, the more options you have. A really, really tiny push over a very long period of time can completely change a hit to a miss, for example. But in any case, even if we have a smaller object, say one that's 100 meters in diameter, if it comes down in the ocean, that causes tsunamis that can flood cities. And so even for the smaller objects, again, having the idea of being able to evacuate is not such a hard problem. But again, we have to know as far ahead of time as possible that this is going to happen. And so that's one of the things that the LSST can help with.
Yeah, it does remind me, I'm not sure if any of the audience members or you, Larry, yourself have seen the movie Don't Look Up. Have you
Yes,
heard?
I have.
Okay, yeah,
Yes.
I mean, as you were talking about it, it was sort of the first thing that was coming to my mind, but I'm glad to hear a little bit of positivity in that case. All right, continuing on with some questions here. It says, how much limitation on ability to do science missions will be created by the satellite mega constellations?
Okay, so there are things that I can say about this, and there are things that I probably shouldn't comment on. The first part is that the Starlink satellites are all in known orbits. So in fact, that's really not such a big problem, right? You have to block out certain parts of the sky that cover the satellite tracks, but that's really a fraction, a small fraction of the sky. So it's not really a big idea that we have to somehow figure out how to get around those. We know where they're going to be, and consequently, we know how to eliminate them from the data set. There's a bigger problem that I can't really go into detail with you about, which is that these huge pictures will also have the tracks of satellites which we don't know about, man-made satellites, right? So you can probably imagine the origin of those. And consequently, it will be the case that we will have to, someone, it won't be me, someone will have to figure out how to eliminate those tracks in cases where there are national security concerns, without letting on that that's what's happened. So it won't be an issue of simply blanking out the pixels where a satellite track went through that's not on the list of satellites that are known. As I say, I can't really go into more details, but there are smart people who are figuring out how to actually eliminate those, which is actually a bigger problem for us, because that means eliminating data without telling the scientists that that's what you've done, and not having it impact the science that they're going to do. So,
yeah, no, that makes a lot of sense. Another question here says, would you please be able to comment on the dangers posed by strange matter and strange stars? Though I believe that these stars are currently theoretical, will the Vera C. Rubin Observatory be able to find them, assuming they exist?
So the answer is possibly, right? So they are theoretical. They do have characteristics that would allow us to distinguish them from normal stars, but they would have to be close enough for us to do that. These are not things that we would be able to see and distinguish a billion light years away or 100 million light years away. So if they're close enough, then, for example, if they happen to exist in the Milky Way, then yeah, we would have a large enough catalog that we could go through and we could look for the characteristics that correspond to these. As far as whether or not they constitute a danger, uh, you know, there are lots of dangers out there that are theoretically motivated. For example, if there's a pulsar that's anywhere close to us and we happen to be within the beam of the pulsar within our galaxy, that pretty much produces enough gamma rays that we would boil away the Earth's atmosphere. So there are lots of potentially dangerous things out there that we just have to hope that space is large enough, and it really is huge, that these are not things that would be an imminent danger to us. The things that are really dangerous are the things that are close by, for example, like the asteroids in the solar system. And so, yeah, we will be able to see any number of strange things that, or odd things, I should say, not strange, odd things out there that are theoretically motivated, as long as we have some way of distinguishing them from everything else.
Interesting. Question here. I'll actually combine them together for the sake because they're kind of similar, but will LSST be able to detect exoplanets or more exoplanets and whether they have atmospheres, and will it be able to search for, I believe it's the Kuiper belt objects?
Kuiper belt objects. So Kuiper belt objects, yes. The Trojans, the Kuiper, we will be able to see pretty much anything above a certain size, certainly 500 meters or larger within the confines of the solar system. In the Kuiper belt, things that are a kilometer or two, all of those will be in the data set, and we'll be able to identify the vast majority of them. Exoplanets we won't be able to do, and that's because we're scanning the sky, right? We're doing a survey. In order to really find things like exoplanets, you would like to have a light bucket that's really concentrated very tightly on an area of the sky that actually has the planet. And then you're going to need to do some really special tricks, like have the planet occluded by its home sun, its star, so that you can look at elemental contributions to the spectra coming through the atmosphere. So that's something that we're uniquely defined not to be able to do, not because it was intentional, but because it's exactly the opposite of what we want, which is you have to stare at a very small section of the sky for a pretty long period of time in order to pick out any properties of something as small as a planet.
Yeah, see, I wouldn't have guessed that, I guess. Another question here says, if the Rubin will see only the sky of the southern hemisphere, will it not be able to observe asteroids in the northern sky?
So we'll be able to see a little bit of the northern sky, but over time, the Earth moves around in its orbit. And so we can actually determine an awful lot of everything that's in the plane. And then over the course of 10 years' time, we actually should see pretty much everything. Now, the reason that's true is because most objects, and certainly any of those that are going to be Earth orbit crossing and dangerous, are going to be in what we call the plane of the ecliptic. That is, most of the objects, like all of the planets, are in a plane that is pretty flat, right? It's slightly tilted. Some objects are a little bit above the plane and some are a little bit below, but pretty much everything that is certainly coincident with the Earth's orbit at some point in time is going to be part of that plane. So that's what allows us to see it from either hemisphere.
Interesting. Yeah, that makes a lot of sense. Question here says, as part of the citizen science aspect of this project, do you plan to use something similar to UC Berkeley's SETI at Home project, which utilizes excess GPU computing power of personal computers to analyze images?
So ultimately, there could be something like that. One of the things that I expect will be explored with Google is a project that maybe is something similar to a kind of SETI at Home or a Zooniverse kind of project. But for the major kinds of contributions to computing that I talked about, processing every night, the 20 trillion measurements that are made, those we're going to plan to have the computing on hand to do. We don't want to leave it up to just how much computing power is actually accessible on any given night in order to look at the throughput. And that's because this really has to be a factory. It has to be a machine that works reliably with known throughput, because the amount of data that we have is going to be really, really large. And so this is a case where the math tells you if you fall behind just a little bit every night, then by the end of 10 years, you've got a really huge problem. You're very far behind. And it's not that things are necessarily going to lose science because of that. It's just that the optimal way to do the science is to make sure that you've identified as many objects in those pictures as possible. And again, you're getting it out to the world so that you're making optimal use of the attention of everybody around the world who has an interest in this in order to look at stuff. So I would say that, yeah, probably there will be some form of a kind of collective community science project around computing power, but what we're planning to do right now is to make a factory that produces data reliably night after night.
That's awesome. That sounds great. Got questions that kind of are similar. I'll just combine them here. It says, will the Rubin Observatory use adaptive optics and will be able to synergize with the James Webb and the Hubble telescopes?
So we probably won't have as much synergy with the Webb, but we will with other space-based telescopes, and that's already being planned. And so there are collaborations and there are scientific internal grants that are being put together right now in order to have us work with various telescope data sets, particularly space-based telescopes, which are the only ones that will be a rival to the LSST in terms of depth. As far as things like adaptive optics, it turns out that you don't really need to make use of adaptive optics when you've got such a wide field of view. Again, I won't get into the technical details of how to do this, but basically the reason you need adaptive optics is because you've got a column of air that you're looking through, and there's water vapor in that air. As well as changes in density, slight changes in density due to winds flowing through. If you've got a large enough field of view, however, you can actually look and compare from place to place within your image to see how much distortion is produced by any given spot on the telescope. So it's actually possible to get a lot of the benefits of doing wavefront corrections, as it's called, from measurements that we can do without having specifically to do with adaptive optics. If you think about it, adaptive optics is really best utilized by a telescope that has a small viewpoint, right? And it's looking at a pretty narrow set of the sky, so that when you're measuring the wavering of light that happens as you go through it with the laser beam, you're also able to turn that directly into correction for the image that comes through that same small area of the sky. If you're trying to do that for the 10 square degrees, right, that just doesn't work, right? I mean, you would have to shine a laser that looks like a spotlight on the sky, and of course that would be not well advised for pilots. So
that's great. Thank you for that. Question here says, NORAD has already been tracking every object from a lost camera an astronaut dropped while on the space station to every satellite in orbit to space junk. Will that information from NORAD be available to the efforts you are describing?
Everything that's publicly available, people are making use of in order to plan out, to not only do mission planning, but to look at impacts on the science. But as I said before, things that are in orbit that are small, they glint and they cause glare and so forth, but they're relatively easy to track and compare to, as I said, things that are in a known database somewhere, and then you just cut them out. So they don't take up a very large area of the sky. So the impact is really pretty minimal for those.
That makes a lot of sense. I guess we have one last question here, and then we'll wrap up about 10 minutes early, let everyone get back to their evening. I think this is a good one to end on. How soon, I know you said it was soon, but how soon will the Rubin be operational?
So I won't give an official answer, but I'm really hopeful that it will be ready to start science operations around the end of 2024.
Great. Well, right around the corner. Years are going by super, super fast right now, it feels like. All right, so I think we'll wrap up here. So thank you everyone for tuning in this evening. And Larry, this was awesome. Great speech tonight. I think all of our audience found it super fascinating. I always love learning about space in these talks. So thank you again. For our audience members, our next Café Sci will be coming up in July. So be on the lookout for our communications, and you can register for that once it gets to you. And with that, I'll let you get back to your Thursday evening, and I look forward to seeing you all next month.
Thanks a lot. Bye, Colin.
All right, bye.